Okay, so 22, a 70 gram piece of metal, 80 degrees Celsius, placed in 100 grams of water at 22 degrees Celsius, containing a calorimeter like that showed in that figure there, and the figure shows a coffee cup calorimeter. So essentially what we're saying is that we have ensured that all the energy that is in the block or in the process transfers to the water. Okay. Okay. So let's see. So if the metal and the water come to the same temperature at 24.6 degrees Celsius, how much heat did the metal give up to the water, and what is the specific heat of the metal? What do you think? Do you know how to solve this one?
I think you did this one in class, kind of like it, right?
Yeah, we did this a couple times. So let me help you with your hair there.
Thank you.
So the water gains all the heat that the block lost. So I can measure how much heat the water gained. That's easy, right? Because I have 100 grams of water, and I know the specific heat of water, 4.184 joules for every gram that goes up a degree Celsius. And I know the change in temperature of the water. What was the change in temperature of the water?
It went from 22 to 24.6.
Yeah, so that's what?
2.6.
2.6 degrees Celsius. So we take the final, 24.6, minus the initial, 22, and that is going to be 2.6, right?
Yeah.
So how much heat did the metal give up? It has to be as much heat as the water gained, right? So I got my 100 times 2.6 times 4.184. Whoops. 100 times 2.6 times 4.184. There we go. All right, so 1,087 joules, all right, those are our units. 1,087 joules of energy. And then from that, we can identify the specific heat of the metal because we know the mass and the change in temperature, and we can solve for the specific heat. What's the mass of the metal?
70 grams.
70 grams. What's the change in temperature of the metal?
How do we determine that? I don't know.
Well, what did it start at?
80 degrees. But I can't tell where it finished.
Well, the water and the metal came to the same temperature.
Oh, okay, yeah, so 24.6 minus 80?
Good. 24.6 minus 80. Now that's going to give us a negative value, 55.4, right? And I can say that the block gave up this energy, so that helps me account for my negative signs. We don't have to think too deeply about that. We know the specific heat for something is always going to be positive. All right, so 1,087 divided by 70 divided by 55.4. Okay, so it looks like it's 0.280. And the units are joules per gram degrees Celsius. That's the specific heat of that metal. And we can check and try to see if we can find a specific heat or what metal has a specific heat of 0.280. Let's see, 0.22 is aluminum, 0.28. I see it in a different spot. It says aluminum is 0.28. So it's probably aluminum. Okay. All right, 23. If a reaction produces that much energy, what is that's trapped in 30 grams of water, initially at 26.5 degrees Celsius, what is the resulting temperature of the water? Okay, so the water goes from 26.5 up to some value, right? And so the change in temperature, we can solve for the change in temperature. If we take 4.184, that's how many joules it would take to change a gram a degree Celsius, and 30 grams of water, and the input energy is 1,506 joules. Can you see that I converted that joules from,
Kilojoules?
yeah, can you see that?
Yeah.
So why did I do that?
We need joules because the specific heat's in joules.
That's right. So this is in joules per gram degree Celsius, so we need joules over here. Okay, so 1,506 divided by our mass, divided by change in temp, or specific heat. So 12, is that one right? 1506 divided by 30 divided by 4. So 12 is our change in temperature, and the 26.5 is going to go up by that 12. So 38.5, what's the resulting temperature? 38.5 degrees Celsius is going to be our resulting temperature. Okay, 24. A half-gram sample of KCl is added to 50 grams of water in a calorimeter. If the temperature decreases, now this is an interesting thing called the heat of solution, right? If I take something, a salt like KCl, and put it into water, it separates into its ions. These are aqueous now, right? And all of the water molecules surround the ions and create new interactions, not actual bonds, but interactions. But every time you create that interaction, you also can release or require heat energy. Now, when we say require, it's relative, again, the formation of these new interactions compared to the KCl, the interactions that are going on here. And in this case, it says the temperature decreases by 1.05.
Why does it get colder?
Well, it's because the interactions that were here were stronger than the new interactions that are formed.
Well, then why does it form?
Well, it's interesting. What we call this kind of a reaction an entropy-driven reaction. Now, we haven't had conversations about entropy yet, but we will in future chapters. But chemical reactions, in this case, for example, the delta H is chemical. It's not really a reaction; it's more of a change, right? Chemical change, chemical adjustment, rearrangement. Delta H's are positive, all right, but the reaction will still occur because the interaction between the chloride and the potassium collectively is stronger than well, it's weightless. It's entropy driven is what we say, the entropy driven reaction. Okay, so the 50 grams of water, though, had a change of 1.05 degrees Celsius, and the specific heat is 4.14 joules per gram degree Celsius. And so this tells us the amount of heat involved in this dissociation. Okay? Does it want, what is the approximate amount of heat involved in dissociation, assuming the specific heat of the resulting solution is 4.18? Okay, so they shifted it just a little bit, but so it's just 50 times 4.18 times 1.05. So 219 joules of energy. If they wanted to know how many joules per gram of material, or per joules per mole, we could divide this by the grams of our KCl, or we could convert that to moles and divide it by moles there. Does that make sense?
Yeah. What about the last bit?
Is the reaction exothermic or endothermic? What do you think? Delta H here is positive or negative?
It got colder, right?
That's right.
So that's endothermic.
That's right. And so the delta H value is positive there. Delta H of what we call solution. This isn't really a reaction the way we generally think of one. Okay, when 1 gram of fructose is burned in a calorimeter, the temperature increases by 1.58. If the heat capacity of the calorimeter is 9.90 kilojoules per degree Celsius, what's the Q for the combustion? So in this case here, we have not a specific heat, but a heat capacity, 9.90 kilojoules for every change in degrees Celsius. And the degrees Celsius is 1.58 degrees Celsius, right? And we don't have to worry about the mass. This just gets us right to kilojoules. So 9.90 times 1.58, 15.64. What are the units there?
Kilojoules.
Right, good. Kilojoules per degree Celsius. That's what our heat capacity was provided, right? So this is in kilojoules. Now, recognize that a heat capacity is for a complex system, not for a specific material. Heat capacity for, sorry, the specific heat and the heat capacity for water, right? When you're just talking about it, you can call it the heat capacity if you want to, but it's 4.184 and it's in units of joules for every gram that changes that degree Celsius. Here, it's just for the whole system, that's how many kilojoules for every degree Celsius. Because the calorimeter is a complex system, lots of materials, right? But somebody did the test and found out that this is how much energy it absorbs for every degree Celsius. Okay, so Q for the combustion is 15.64 kilojoules. And if we wanted to convert that to kilojoule, or not convert it to, but identify kilojoules per mole, right? We could say 1 gram of fructose divided by the molar mass, 180, and take our kilojoules here and divide it by the moles, and that will be kilojoules per every mole. Okay, when that many grams of TNT, trinitrotoluene, is burned in a bomb calorimeter, the temperature increases from that to that. Heat capacity of calorimeter is that. It contains that much water. Well, we don't care about how much water it contains. If this is the known heat capacity, let's see, is that going to make any sense? 4.184 times 675. Yeah, we have to include both those energies because that 534 joules per degree Celsius doesn't include the water.
How do you know?
Because if it was just the water itself, 675 milliliters of water, then it would be that much energy.
Oh, I see.
So I have to add those together. So there's 2,824. I got that by taking 675 times 4.184, right? That's how many joules it takes to raise 1 degree Celsius, plus the 534 for the calorimeter itself. So this is our, what we call our heat capacity for this system. It's 3,358 joules for every degree Celsius that's going to change. This is the sum of the water's capacity, heat capacity, and the calorimeter's heat capacity. Okay? And it changes from 23.4 to 26.9. How do we find the change in temperature?
26.9 minus 23.4?
Yeah. Initial minus final, right?
Well, final minus initial.
Yeah, final minus initial, sorry. So 26.9 minus 23.4, 3.5 times our heat capacity. So that's going to be 11.8 kilojoules of energy. How much was produced? Yep, and there's the answer. If we wanted to divide it by the moles of TNT, we could take this, divide it by the molar mass of this, and convert it to moles. Take those moles and divide it by that. Okay, 45. Why don't you read that one, Fred?
How much heat is produced by burning 4 moles of acetylene under standard state conditions? Acetylene?
Yeah, so we're burning acetylene, and we want to know how much energy is produced when we burn it. Okay, so acetylene, C2H4, combines with oxygen gas to form CO2 and water. We need this balanced. 2 there, 2 there, 1, 2, 3, 4, 2 there. No, it's 1, it's 4, 5, 6 there, so we need 3 there. Okay, so there it's balanced. C2H4, that's acetylene. We could look that up, right? That's not that big of a deal if we don't know what that is. We could look up the combustion of acetylene with oxygen. How much is produced when we burn 4 moles? Well, we need to know the delta H. What's the delta H for the combustion of acetylene? Okay. There we got it. So we're burning 4 moles, so it's that value times 4. 1300 times 4, 5,200 kilojoules for burning 4 moles of acetylene. Okay, 46, Fred.
How much heat is produced by the combustion of 1.25 grams of methanol under standard state conditions?
Okay, so we're burning methanol now. All right. If we burn methanol, CH3OH, I mean, you can look on a table. Let's see if we go to the table in our book really quick. We're going to burn methanol. We're going to combine it with oxygen and form what?
Carbon dioxide and water.
Very good. We got to balance this. 1 carbon there, 4 hydrogens, so 2 of that gives us 4 hydrogens. That's 1, 2, 3, 4. So 2 of those will give us 4. Oh no, I have one more. I have 4 hydrogens, but I have 1 more oxygen here. So I have 1, 2, 3, 4. 1, 2, 3, 4. So I only need 3 here. So I need 3 halves. That's 1.5 times 2, right? So 3 divided by 2 times 2, yeah, that's 3. Okay, so we got 4 altogether. So I need to multiply this by 2, and this goes 3, 2, 2, 4. Okay, there we go. So we got this equation balanced, 2, 3, 2, 4, and we're going to see how much heat is produced by the combustion of 125 grams of methanol under standard state conditions. Well, what's the delta H for the combustion of methanol? Enthalpy of combustion. Enthalpy of combustion, is this for methanol? Yeah, this is for methanol's data page. So, do we see it? Methanol.
That's it, right?
Oh yeah, right here. Enthalpy of combustion, 715 kilojoules for every mole. So this is 2 moles. So 715 times 2, 1430 kilojoules, negative 1430. That's delta H for that reaction. Delta H, negative 1430. Okay, so if I start off with 125 grams of methanol, and I want to know how much heat, we can go in kilojoules probably, right? I can go from grams to moles of methanol. And then I can go from moles of methanol to moles of methanol produces 1,430 kilojoules of heat. All right, so I just need to find the molar mass of methanol. Molar mass of methanol.
Molar mass of methanol is 32.04 grams per mole.
All right, 125 divided by 32.04 times 1430 divided by 2. Okay, so 2,789 kilojoules of energy. 125 divided by 32 times 1430 divided by 2. Okay, good. Isooctane must be burned to produce 100 kilojoules of heat. How much isooctane? We can look into our book here. In our book, they have a nice table for us for all the delta H of combustions, not all of them, but a lot of the delta H of combustions. And I'm sure that instead of having to look on Google, we'll see it in here. Here it is, isooctane. 1 mole of isooctane burns to form 5,461 kilojoules for every mole of this isooctane. Okay, so We want to know how many moles of isooctane. 5,461. We want to know how many moles of isooctane are going to be produced by doing what?
We want to know how much isooctane is required to get 100 kilojoules of energy.
Okay, so moles of isooctane, and we're producing 100 kilojoules of energy. And we know that 5,461 kilojoules is what I get when I burn 1 mole of isooctane. And then I can relate, what do I want? Oh, that's it. I just want moles of isooctane. So 100 divided by 5,461. Is that in kilojoules?
What in kilojoules?
5,461.
Oh yeah, it's in kilojoules.
Yeah, it says right there, kilojoules per mole. Okay. So I only need 0.183 moles of isooctane to get the job done, right?
Sounds good.
What mass of carbon monoxide must be burned to produce 175 kilojoules of heat under standard state conditions?
You can burn carbon monoxide.
Yep, here it is, right here. See, burning carbon monoxide releases 283 kilojoules for every mole. Okay, so if I'm releasing 283 kilojoules for every mole of carbon monoxide, what mass of carbon dioxide must be burned to produce 175 kilojoules?
Start with moles of carbon dioxide.
Well, I just know that 283 kilojoules is released for every mole of carbon dioxide. And then I can just say, if I have, no, sorry, start over. What mass of carbon dioxide, grams of carbon monoxide, all right, and I'm going to start with 175 kilojoules. And I want to know how many kilojoules for every mole of carbon monoxide. And then I can go from mole of carbon monoxide to grams of carbon monoxide. What is that? 12 plus 16.
43.8.
12 plus 16? 28. 28 grams for every mole. And then, what's this? Kilojoules per mole of carbon monoxide?
It's the 283.
Okay, let's see. Did you get that from the that chart there?
Yeah.
283 kilojoules per mole, right? Okay, good. So 1 mole of carbon monoxide burning releases 283 kilojoules. So 175 divided by 283 times 28. Okay, so that's 17.3 grams of carbon monoxide. Okay. Okay, that's a good place to stop for now.